we will look at the 4 position synthesis for motion generation. Now, if you remember, in the graphical methods we stopped with 3, right, because we ended up with a unique solution. So, essentially the strategy that we used was, okay, the moving pivot will move along a circular path. So, up to 3 positions I can find the center of the circle that passes through those 3 points, and then I am, so but I ended up with a unique solution in that case. But if you look at the table that we did for, when we looked at the Dyad synthesis method, and you look at so if you look at a Dyad, e power I phi 2 minus 1 gamma 2 minus 1 equal to delta 2. You have what is given are the deltas and the gammas, because this is a motion generation problem, and your unknowns are Z1, Z2, then phi 2, phi 3, phi 4. Okay. So, equal to 7 scalar unknowns. You have 6 scalar equations above, 7 scalar unknowns. Therefore, you still have one free choice, okay, which means theoretically you should have an infinity of solutions, right. But we saw with the graphical method that we ended up with a unique solution for the 3 position problem, and we did not explore the 4 position, although some clue you have, like for instance if you take the pole, okay, if you take for 2 positions, if you take the pole say P12 as one of your moving pivots. Now, what happens in position 1 and position 2, the location of that does not change. So, I can actually, if I choose that as a moving pivot, I can actually reduce the 4 position problem to a 3 position problem, because one point does not change between 2 positions. Okay. So, there are graphical methods, it is called point position reduction. Okay. There are graphical methods, but we did not go into that. Essentially you do have, we saw that you do have a free choice. The question is, how do we exercise that free choice, maybe not graphically, but how do we solve this problem. So, we should have an infinity of solutions. So, we saw that the strategy was, okay. So, if you take the 4 position problem, okay, if you take 4 positions of this thing in the plane of the coupler, and I find corresponding, say for the 3 positions I find OA and some OB. I am just drawing it randomly, but say I find the corresponding center points, right, for these 3 positions. if I take say 1, 2, 3 and then I take 2, 3, 4, the odds that OA and OB will, that A4 will also, A4 and B4 will also lie on the circle passing through OA and OB, you know, which satisfies the first 3 position, is very low. Okay. So, that is not going to happen. So, if I synthesize for 3 positions and add a third position, it is not likely that the fourth one is going to be on that same circle, right. So, the question we want to ask is, are there certain points on the coupler or the moving plane such that you can find a circle that passes through all 4 of them, so that they will lie on the same circle. So, are there points K in the coupler plane such that its corresponding four positions lie on a circle centered in the fixed plane centered in the fixed plane for the 4 arbitrary positions of the coupler. For arbitrarily prescribed. That is my design condition, right. I give 4 positions based on some other criteria, but can I now find, can I find points on the coupler such that they would still lie on a circle centered in the fixed plane. Okay. So, that is the task that we have. So, this question was asked by Burmester. So, this theory is called Burmester theory in 1876, and he figured out the solution to this as well. So, the Burmester theory was proposed in 1876, which basically deals with the 4 position problem of motion generation. So, now let us go back to the equations. You should be able to write these equations in your sleep now. The standard form e power I phi 4 minus 1 delta 4, right. So, here the unknown angles, okay. So, the unknowns are Z1, Z2, phi 3, phi 4, and the unknown angles are in transcendental form. Okay. You do not have up to 3 positions. We saw we got a nice set of linear equations that we could solve for the dyad, right. Now, that is no longer the case. Okay. We saw that even with the in the case of specifying the fixed pivot, even for the 3 position problem, if you specify the fixed pivot, then you actually get, you have to satisfy a condition, a compatibility condition, so that which is transcendental in form. Okay, and we did that with the using geometry, right, forming that triangle. We had that d1 plus d2 e to the power phi 2 plus d3 e to the power phi 3. Okay. So, you have already seen that kind of a form. This is sort of an extension of that. So, you will see here that these angles are in transcendental form, and therefore, these equations are not easily solvable. Also, you have only you want to really solve for z1 and z2, those are what and you have only one free choice, but no matter what I pick as my free choice, the other angles are still unknown. Okay. So, the three unknown therefore, you need some kind of a non-linear technique. So, I can write this in matrix form. I can write this set of equations as okay, the same equations can be written in this form. Okay, same thing. So, this is if I want this system to have a solution for z1 and z2, okay, then the determinant of my augmented matrix has to be 0. So, that is an additional condition that I have to satisfy, right. So, that means two of these equations should be linearly dependent, right. I can have only two sets of linearly independent equations out of the 3. So, the coefficients must satisfy certain what we call compatibility conditions. So, the compatibility condition for this becomes basically you are saying the rank must be 2, right. So, the determinant of the augmented matrix should be 2. So, I can first write this as no, I won't write that. Okay. So, the solution to that exists only if this determinant minus 1 e power I gamma 4 minus 1 delta 4 equal to 0. So, this is the determinant of that matrix. So, I have only one free choice. Okay. Let us say I take, let my free choice be phi 2. So, in this the second column everything is known because gamma 2, gamma 3, gamma 4 are specified. Again third column delta 2, delta 3, delta 4 are specified. So, let my free choice be phi 2. So, I will expand about the first column. Okay. So, I can say delta gamma 3 minus 1 minus delta 3. Remember delta, all these are complex numbers, the deltas, and so are the e to the power I gamma 2, gamma 3 etc. Okay. Minus, I will expand about the first column because that is where the unknowns are. Plus e to the power gamma 2 if I expand these and simplify, I get, I will use delta 2 e power I phi 2 plus delta 3 e power I phi 3 plus delta 4 e power I phi 4 plus delta 1 equal to 0, where delta 1 is based on the first position minus delta 2 minus delta 3 minus delta 4. This is what I get if I expand this. Okay. I get this in this form. What does this form remind you of? Remember, these are all complex numbers. Does that look familiar? This looks like the loop closure equation for a 4 bar with fixed length delta 1 and the other 3 links delta 2, delta 3, delta 4. Okay. So, if I take phi 2 as my free choice, that becomes the input to this 4 bar. Do you see that? So, this is, so in the first position it is delta 1 plus delta 2 plus delta 3 plus delta 4 equal to 0. That is my loop closure equation. Then I give everything a rotation. Delta 2 I rotate by phi 2, delta 3 then rotates by phi 3 and delta 4 rotates by phi 4, and still the loop is closed, which is just like your 4 bar. This is a different 4 bar. This is a 4 bar. We are not talking about the 4 bar that we are trying to synthesize. Okay. So, this is basically the compatibility condition can be thought of as a 4 bar satisfying this loop closure equation, where the lengths are basically delta 1, delta 2, delta 3 and delta 4, and all these deltas are based on known quantities. So, let us write that. So, delta 2 is, these are basically the cofactors. Sorry. Delta 4, delta 3 equals and delta 3, sorry, delta 4 and delta 1 equal to minus delta 2 minus delta 3 minus delta 4. All the deltas are known. Why? Because they contain only input data. All the gammas and deltas are known. So, all 4 deltas are known. So, this condition, this delta 1 plus delta 2 e power I phi 2 plus delta 3 e power I phi 3 plus delta 4 e power I phi 4 equal to 0 is the compatibility condition. What that says is, I can choose this phi 2, phi 3, phi 4 have to satisfy this condition. I can choose my phi 2 and then my phi 3 and phi 4 get determined by this condition. So, I cannot use any random group of phi 2, phi 3, phi 4 for my solutions, right. For a particular phi 2, phi 3 and phi 4 should satisfy this condition in order for me to have a solution for Z1 and Z2. That is what this essentially tells me. Okay. So, this resembles a loop closure equation for a 4 bar formed by delta 1, delta 2, I can mod of, if I take those as the link lengths, right. So, in the first position I have delta 1 plus some delta 2 plus delta 3 delta 4, that is equal to 0. Okay. Now, I rotate, if this vector I rotate by some amount, okay, then this vector becomes, delta 1 remains the same, it is the fixed link of this 4 bar. You see there is no phi 1, there is no angle associated with that, it depends on, I can think of that as a constant, and then this can be thought of as, okay. So, this would be delta 3 e power I phi 3, this would be delta 2 e power I phi 2, and this would be delta 4 e power I phi 4, where the angle is from the origin. Okay. So, I can think of it in the this way. So, I can use this. So, it is essentially solving for the other 2 angles in the 4 bar. Okay. By now, if you do not have that code, you probably want to create that code for, this is the position analysis code for a 4 bar, to find those angles and to draw the 4 bar in that position. Okay. So, because that is the reason you are going to use it again and again, this code, okay, for this. You can also look at this as, because phi 2 is your input, your free choice, I can also use the same code that I wrote for my other one, that D1 plus D2 plus D3 for the fixed pivot, because this vector I can take it and I can call it repeatedly. I can check compatibility by doing that, because this then becomes a known quantity, right. So, I can look at this as delta 1 dash equal to delta 1 plus delta 2 e power I phi 2. So, I can say delta 1 dash plus delta 2 e power I phi 3 plus delta 3 plus delta 4 e power I phi 4 equal to 0, which is what I used for the previous, for my where I specified the fixed pivot. Remember, I had to solve a transcendental equation there. So, you can repeatedly call that for each phi 2. That is another way you could do that, but I think it is useful to have this 4 bar position analysis code. It is useful for you to do that. And the circ command makes it really easy to write. So, you solve this compatibility condition, and then so for each phi 2 I will get what? I will get a phi 3, phi 4 and a phi 3 dash, phi 4 dash. Why? Because of my 2 assembly modes for the linkage. Okay. Because of the 2 assembly modes for the linkage, I will get these sets. Okay. So, if assembly mode 1, if it is phi 3, phi 4, assembly mode 2, I will get phi 3 dash, phi 4 dash. Okay. So, then once I get this, I can use 2 of these equations, 2 out of the 3 equations, because now I will have the specific phi 2, phi 3 combinations that will work, that will satisfy the compatibility condition. So, I can take any 2 of these equations, plug in the phi 2, phi 3, or depending on which equations I choose, and find the Z1 and Z2. Then it becomes just a linear system. See, earlier we were able to, like for the 2 position problem, right, we were able to pick phi 2 and phi 3 as free choices and solve for Z1 and Z2, for the 3 position problem. Okay. For the 3 position problem, we picked phi 2 and phi 3 as free choices, made this a linear system of equations in Z1 and Z2. Now, I can't choose arbitrary phi 2 and phi 3, I can choose phi 2 and phi 3 such that it satisfies that compatibility condition, okay, which means essentially solving for that 4 bar. So, specific values, specific combinations will give me solutions for this. Phi 2, how many choices do I have? I have an infinity of choices. So, again I can technically solve the 4 position problem. I do have an infinity of choices. So, I should have an infinity of solutions. So, I will just show you. So, this is my coordinate system. I have this point P. I have solved for Z1 and Z2. I can basically find, so I will call this point circle point in the first position. So, I will call it K1. This is the fixed point. Remember, M for middle punct. So, it is the middle center point. Okay. So, and K is the circle point. So, I can, so this vector M will define that and K1. Okay. So, I can my circle point, this is R1, right, which is known. my first position, my first precision point. This should be P1. So, circle point K1 is defined as R1 minus Z2. Okay. R1 minus Z2 is K1, and then my center point, moving pivot or my center point or fixed pivot, M is K1 minus Z1. All these are vectors, so I will just okay. So, this set this combination of K and M, it is called a Burmester point pair. Okay. So, BPP, Burmester point pair. Because it says that for a specific circle. So, if I find the locus of all the points K1, okay. So, see, I have found out Z1 and Z2, I have solved it for different values of phi 2. Okay. I have taken phi 2 as my free choice, I have solved the compatibility condition. So, I have sets phi 2, phi 3, phi 4, I have several sets of those. Using that, for each set I can find a Z1 and Z2, correct. So, from that if I find, so now I have the locus, if I plot all those points, okay, I get a locus of all the possible circle points, okay, for which I can hit these 4 positions. And for each of those circle points, there is a specific center point which is determined by this relationship. So, I can choose my circle point, I can, so once I draw the curve of all possible circle points, once I choose a circle point, which means I specify my K1, then M becomes completely determined, because M equals K1 minus Z1. I have solved for Z1 and Z2. Okay. So, for each circle point there is a corresponding center point, or for other way around also. I can choose, so I can choose my fixed pivot instead. I can choose my center point in the fixed plane, in which case I will know exactly where my circle point is going to be once I plot the locus of these points. So, I will just show you. So, a plot of the, okay, let me just write this down and then, okay. So, you get 2 sets of the Burmester point pairs. Why 2 sets? Because again phi 3, phi 4, phi 3 dash, phi 4 dash. So, for 2 sets, one for phi 3, phi 4, one for phi 3 dash and phi 4 dash, with phi 2 being varied. So, for each phi 2 you will get 2 sets of Burmester point pairs. So, a plot of the center points for each value of phi 2 will give you 2 branches of the center point curve, one for the compatibility equation in mode 1, the other for the compatibility equation in mode 2. Center point curve is called the M curve. because one branch is associated with phi 3 phi 4, another with phi 3 dash phi 4 dash. So, if the compatibility linkage, if that allows complete rotation of the delta 2, then the two branches will meet, okay, and I will show you that. Do not confuse the compatibility linkage with the linkage that you are trying to design. Okay. So, and similarly you can plot the circle points can also be plotted to give the circle point curve, K curve. So, every point on the center curve or the M curve is a potential fixed pivot, right. Every point on the M curve is a potential fixed pivot. Therefore, now you have an infinity of solutions as long as it lies on that curve. You pick a point on that curve, there are an infinity of points on a curve. So, any point that you pick can be is a potential solution for the fixed pivot. Once you do that, the corresponding circle point gets fixed. So, you cannot pick any point on the center curve and any point on the circle point curve. You can choose one or the other, because only then your compatibility condition will be solved. Okay. So, then you can form dyad for one side. Similarly, choose another center point on the curve, find the corresponding circle point, you have a second dyad, you can form your 4 bar. Okay. So, let me just show you. So, here we can program the equations for the 4 position synthesis, the equations that we just derived, and then use MATLAB or some such language to plot the M and K curves for a particular set of 4 position motion generation problem. So, here for instance, we have these are the 4 positions P1, P2, P3 and P4 defined by these position vectors, and the orientation of the coupler plane in the from the first position are also given in terms of gamma 2, gamma 3 and gamma 4. So, for this problem this here is your, I have put circles here. So, this is your K curve or circle point curve, and this one here is the M or center point curve. What this means is I can now pick let us say center point is usually is convenient to pick. So, I could pick any point on this M curve, and then that would have a corresponding point on the K curve that can be used to construct the linkage. So, for instance, here I have an example. You can see here I have picked for one dyad. So, this is a center point that I have picked on this curve, and that has a corresponding circle point here. Then the other one I pick for the other diode, I have picked a center point here, and that has a corresponding circle point there. So, my two diodes, for one I have a diode say Z1 and Z2, this is one diode, and then the other diode would be say Z3 and Z4. So, these are the two diodes I have solved for, and this becomes my linkage. So, my coupler is the triangle formed by these. So, that is my coupler triangle. You can see this is the position 1. These are the points, the circle points in position 1. Okay. So, I will call that K1 and this as K1 dash. Okay. The circle point corresponding to this center point. So, this is M1 and this is M, let us just call this M and M dash. Okay. So, M is the center point which I pick on this curve, which has the corresponding circle point K1 on that other curve, and so I can construct my linkage with these two diodes. So, this I have plotted the circle and center point curve for one mode of the compatibility linkage. So, that has nothing to do with whether this what mode this linkage is in the final solution. The M and K curves that I have plotted here are for one mode of the compatibility linkage. So, if I look here, I have plotted this for both modes. So, this is the K curve for mode 1, meaning in the compatibility equation for a particular phi 2, as I vary phi 2, I get a phi 3 and phi 4, and that is my mode 1. This is the K curve and this is the M curve for mode 1. And I can also plot for mode 2, which means for this is my K curve for mode 2, where when I vary phi 2 I get phi 3 dash, the other set of solutions for phi 3 and phi 4. So, phi 3 dash and phi 4 dash, that is my mode 2, and I get this as the center point curve and this as the circle point curve, circle point or sorry the center point curve. This is the, so this is the K curve, the circle point curve, and this is the M curve. Sorry, this is correct, middle circle point, this is the K curve, correct. That is the K curve, that is the M curve for this. Again for the same 4 position problem, 4 position motion generation problem, these are the two modes. Now, if the compatibility linkage is capable of making a complete rotation, like if delta 2 in that compatibility equation can do a full 360 degrees, these two curves would meet. Okay, here they do meet, except that I did not plot them because the scale blew up for something else. So, I something else went, this went up to like 10 to the power 15. So, I had to, so you would not be able to see the curves at all. So, I did not plot it here, but if the two ends for the two modes, if the two curves meet, the corresponding M curve or K curve, if they meet, then that means the compatibility linkage is capable of making a full rotation. Of course, that has no bearing on whether the final linkage will be able to do that. Okay, you have to be able to separate out what the compatibility, what the so called compatibility linkage, it is not really, we saw the form as that of a linkage and hence interpreted it that way, but really the final solution is the linkage that you design from these k or m curves. So, you can see there will be an infinity of solutions. So, say I choose a center point, then I have an infinity of solutions for the center point, and but once I choose the center point, it has only one corresponding circle point or vice versa. If the circle point is chosen, I have an infinity of choices for the circle point, as you can see from the curve, and it would have only a single center point associated with that. So, for the two dyads you would have, so infinity of solutions for one dyad, and to form the linkage you need two dyads to form the linkage. So, you will have infinity square solutions for the linkage. Okay. So, this again shows two dyads that I have chosen, again center point, circle point, and the circle point, and this is the coupler which reaches position 1, 2. We even in this method of synthesis we have no way of knowing about the final linkages behavior in between the positions. We know that it can be assembled in those 4 positions. You will still have to simulate the linkage or make a model or something to ensure that it reaches the 4 positions that you want it to reach in the order that you want it to reach, and to make sure that it reaches all the points, because there could be problems with branching where one position lies on one mode of the linkage, the other 3 positions may lie on some other on the other mode of the linkage, etc. So, the synthesis, solving the equations and generating the center point and circle point curves tells you this. There are some, if you there is some research that will show you how you can choose on the circle and center point curves to avoid some of these problems with the order problem or the branch problem, etc. So, you can look that up if that is of interest to you. There is literature out there that will that looks at how the how you can choose on the center point and circle point curves. So, here is another example of different set of 4 positions. Again you can see this is the M curve and K curve, and I can choose a center point which has a corresponding circle point. Another center point that I choose has this as the circle point, and so this is the coupler of my linkage. So, the 2 dyads, the pink dyad and the black dyad, together they form a 4 bar, which will, these are the positions. This is P3. Okay. This also gives you a clue on how you could approach a 5 position synthesis problem. So, if you had, also gives you a clue on how to approach a 5 position synthesis problem. So, if you had to reach 5 positions, say defined by these vectors and the orientations here, then you can plot the m and m curves. So, this one shows the m curves in the two modes. You can plot the m curves for 4 positions at a time, and then if when you do that, if there are intersections, then those are potential solutions for the 5 position problem. So, that is one way to look at solving a 5 position problem. You can also use the same methodology to solve for a slider crank, where you only need one dyad. So, here I have these 4 positions which are in a straight line. So, I have P4, we have a slider crank with these 4, we want to design a slider crank. So, I draw the m and k curves, find a dyad which will give me a slider crank that can move through these 4 points in a straight line. So, this kind of explains, the coding takes quite a bit of effort. I mean, we go through it very quickly here, but the coding takes a good bit of effort to get the m and k curves, but it is a useful design tool. And you can also those of you who are experienced programmers can also you can actually choose these points on the screen and automatically have it pick the point closest to where you choose with the cursor, and then get the corresponding center or circle point for that and construct the linkage. So, this concludes what I wanted to do about the m and k curves for 4 position synthesis and the Burmester point pair. So, the pair of circle and center points are called the Burmester point pairs, as I had mentioned before. Okay.